Okay, we're going to start our new unit today. This is Unit 4, Trig Identities. Just want to go over the calendar. To begin with, we are, thank you. We'll be going through notes for this entire week. And we're going to be having a quiz next Tuesday. So we'll definitely have Monday as a review day, next Tuesday being the quiz, and then and the following Tuesday will be our Unit 4 Part 1 test. So Trig Identities, it's kind of a long unit, so we're splitting it into two subunits. So the packet that you have in front of you is the first part of chapter of Unit 4. And then we'll move into the second part for the remainder of the semester. So the remainder of the semester, we just have one unit remaining, but it's such a long unit, we're splitting into two parts. Okay. Now, also, the back of your calendar has a formula sheet. Okay, so this formula sheet we'll be referring to quite a bit. So I think it's good to have this on hand, so as we're working in the packet, you don't have to kind of flip back and forth. We can refer to this formula sheet. So it just makes it hopefully a little bit easier, so you don't have to go back and forth. Okay. All right, so we're going to start off with notes. I will have you guys have something for you guys to copy down. You guys can spend a minute to copy this down. Some of these reciprocal identities you already know. I think a lot of this it's gonna feel familiar because you've seen it ever since unit circle. We're just going to be looking at it from an equation standpoint. This is also on your formula sheet. Well, the reciprocal identities are. So what is an identity? Identity is an equality that is true. It holds true for every value of that variable. The variable that we're going to use the most often is x and theta. It just depends on the problem. But really, it's interchangeable. Sometimes problems are presented in terms of x. Sometimes the variable is presented as theta. Reciprocal identities, we know from unit circle, but basically sine and cosecant are reciprocals of each other. Cosine and secant are reciprocals, tangent and cotangent, and vice versa as well, right? Cosecant is the reciprocal of sine, secant is the reciprocal of cosine, cotangent is the reciprocal of tangent. Okay, look at part A. Given that cosine is equal to 4/5, what do you think secant will be? Yeah, just 5/4, right? We don't have to go through the trouble of saying 1/4/5. We just know that secant is the reciprocal of cosine, so we can jump directly to it being 5/4. Sine of x equals -√8/4. What's cosecant of x? Yeah, -4/√8, but we can clean that √8 up, right? So we can first make it -4/√8, but then we can rationalize the denominator, multiply numerator denominator by √8, or you can clean up that √8 first, make it -2√2. And once you're down to 2√2, we can reduce even further. We know -4 and 2 can reduce to be -2, so -2/√2. Further rationalize this denominator, multiply numerator denominator by √2. So √2/√2, we get -2√2/2, and the 2's can cancel out. We're left with just -√2. Okay, tangent of x equals -1/4, therefore cotangent must be -4. Yeah. Okay, does anybody still need to look at A, B, or C? Okay, quotient identities. These are involving tangent and cotangent. So tangent we know is 1/cotangent, but tangent can also be represented as sine over cosine. That's going to be extremely helpful and useful for us when we're having to clean up our expression. A lot of times, something that really helps is converting everything to be in terms of sine and cosine. We know we can convert cosecant to be in terms of sine. We know we can convert secant to be in terms of cosine. But tangent and cotangent can also be turned into sine and cosine. So if tangent is sine over cosine, what do you think is a way to represent cotangent? Yeah, it's the reciprocal of tangent, which if tangent is sine over cosine, we can also think of cotangent as cosine over sine. Okay, so these are extremely helpful identities that will help us through reducing, simplifying certain problems. Okay, we have something called, these are Pythagorean identities. Okay, there's actually 3 of them, but I will say that there's one that's more important than the other, because if we can memorize one of these, then the other 2 we don't have to memorize, we just have to know how to derive them. Okay. So imagine we can go back to unit circle. Unit circle is where your radius of your circle is 1. And we knew that any order pair that we found, the first value of the order pair represented the cosine, right? And the second value of that order pair represented sine. So think of x and y as cosine and sine, and that's what we can represent here. So if this is theta, we can think of the x portion as cosine, and think of the y portion as sine. Now, we have a right triangle in front of us. What I want to show is that there is a Pythagorean theorem that we can create out of these equations, or out of these variables here. Now, Pythagorean theorem, you're used to seeing a squared plus b squared equals c squared. Leg squared plus leg squared equals hypotenuse squared for a right triangle. We can adapt it for cosine and sine. So we'll say cosine of theta squared plus sine of theta squared equals 1 squared. Okay, everybody okay with that? Okay. Now, I want to talk about something here. Cosine theta squared, this is perfectly fine. But typically, the way that the book writes it, a lot of the way that we write it is a shorthand form of this. It means the same thing, but if we write it this way, we don't have to use as many parentheses. So typically, what you're going to see is sticking that squared between the cosine and the theta. But I don't want us to be confused and think of this as something meaning that we're squaring the theta or squaring the cosine but not the theta. This is just a shorthand way of writing this, just so that we don't have to use as many parentheses, right? This means that we are squaring the entire cosine of theta, just like how we do here. Okay. So just as a reminder, this means cosine theta times cosine theta. So just as another reminder here, cosine theta times cosine of theta, we write it as cosine squared theta. So that 2 is specifically placed there to represent that shorthand form. What you don't want to do is you don't want to say cosine of theta times cosine of theta is equal to cosine of theta squared. That's something different. Okay, if you write it as cosine theta, cosine of theta squared, that means you're squaring the theta but not the cosine. So there's a distinct difference between this notation and this notation. This is a shorthand way of writing out, I want the entire expression squared. If I put that squared next to theta, that means I'm only squaring the theta inside that cosine function. Typically, though, we just for memorization purposes, we should think of it as cosine or sine squared plus cosine squared equals 1. They mean the same thing, just typically we see it in this form rather than this form. But you know, adding terms doesn't, the order is not going to matter. Okay. Okay, put a star next to this one. This one you definitely want to be able to memorize because you're going to use this a lot. Now there are 2 more identities, and these are ones that even I don't memorize these, I just know how to derive them. So let me talk about how we can arrive at 2 more identities that's very much related to this. Okay, so this is how I derive them. I start off with what I know. And one of the identities is produced by just dividing by sine squared. So I'm going to take the identity that I already know. I'm going to divide everything by sine squared. And then what is going to result is going to be another identity that we're going to find very useful. So let's see if we can clean this up, just seeing what we have in front of us. What do you think sine squared over sine squared can reduce to be? Just 1. Okay. What do you think cosine squared over sine squared can be represented as? Good. So you see, cotangent is cosine over sine. We just talked about that. So I'm going to represent this as cotangent squared. Do you know, is there a trig function that's represented by 1 over sine squared? Yeah, cosecant, right? Because we know that 1 over sine is cosecant, right? Sorry. Okay, so this is the second one. So again, I really don't think there's there's a need to memorize this because you can just quickly derive, as long as you know sine squared plus cosine squared equals 1, you can get to the to one of them, right? So divide everything by sine squared, and you should be able to arrive at this other identity that we're going to find very useful, depending on the problem. Okay. Okay. So there's a third one as well. That third one, you can guess, instead of dividing everything by sine squared, we'll divide everything by cosine squared. Okay, let's see what comes out of this one here. What's sine squared over cosine squared? Tangent, yep. Cosine squared over cosine squared? 1. 1 over cosine squared. Secant squared. This is the third trig identity that will be very useful. But I don't think it's necessary to memorize these. As long as you know this one, you can quickly arrive at these two. Okay, so these are the ones that we're really going to work on and use as we look to simplify these different expressions we're going to see on the next page. Okay, everybody have a chance to copy this down. Okay, let's go to the bottom portion here. Okay, given cosine of x equals 3/4, find sine of x. Use Pythagorean theorem. So let's go ahead and draw our triangle. Cosine is adjacent over hypotenuse. So adjacent over hypotenuse. Pythagorean theorem, a squared plus b squared equals c squared. I'll call this b. And now I'm just going to set it up. So we can't, this is not quite a 3, 4, 5 triangle, right? 3, 4, 5 triangle would need a 5 to be in the hypotenuse side of things. But so it's not going to be a pretty number here. It's going to most likely be a radical. Nine plus b squared equals 16. Subtract 9 from both sides. B squared equals 7. Take the square roots. B is equal to root 7. Okay, so therefore, what's sine of x going to be, or sine of theta? Sorry, I changed the variable midway through. Sine of theta equals, if b is root 7. Yep, opposite over hypotenuse. Sorry, I changed the variable midway, but sometimes they give you theta, sometimes they give you x. So whatever the variable they give you, you're just going to use that one. I should have just stayed with x. Part B just says use the Pythagorean identity. So just so that we can get some practice with the identity, we know one of the identity we can use is sine squared x plus cosine squared x equals 1, right? This is built off of the Pythagorean theorem. So we know cosine squared. Cosine of x is 3/4. So I'm going to replace cosine of x with 3/4 and square that. I'm going to solve for sine this way. I'll get the same answer, but it's just, instead of using a triangle, I'm using the identity. Okay, so cosine is 3/4. I'm going to square that, 3/4 squared. All right, I'm just trying to find sine of x, so I will subtract the 9/16 from both sides, and I can deal with the square root. It's basically 16/16 minus 9/16, which is 7/16. Root 7/16, does that end up being the same thing? Yes. All right, questions so far? All right, next page, page 3. Okay, so the problems that we're going to learn how to solve is simplifying. Sorry about that being cut off there. Simplifying, we want to write it in simplest terms, depending on, so taking a complex expression and using identities and properties to try to clean everything up, cancel and reduce. Another type is verifying. This is showing why the identity is true by working from one side to the other. So we'll definitely get to this later on in the week and also for the remainder of this unit. And then evaluating. This is using trig identities to solve. But I think right now we're just focused mainly on the simplifying portion. Learning, building our knowledge of how things work, and we can kind of build from there. So here are some strategies for simplifying and verifying trig identities. Okay. We can use the correct identity. Sine of x, cotangent of x. What's another way of writing that? Well, we can rewrite everything in terms of sine and cosine. That's a quick way to kind of get some matching parts and to see what the relationship is, right? So sine of x, we'll leave that alone, but we can think of cotangent of x as what? Yes, 1/tangent, but is there something else that we can do that's maybe more helpful? Cotangent can be written as, yeah, it does involve sine and cosine. Good, cosine over sine. So if you go and look at, you have it here under your trig identities on the back of your calendar. We can kind of refer to it as well, right? Cotangent is cosine over sine. Okay, so I'm going to replace cotangent as if it helps, you may want to put a 1 underneath sine, just so you can kind of match all the parts here. We got sine of x over 1 times cosine of x over sine of x. What do you see here? Anything that we can do to reduce this? Yeah, we can just get the sine x to cancel out, right? Numerator and denominator, if they match, we can just remove them. There's no addition or subtracting preventing us from moving forward. We can just cancel those out. It's like sine of x over sine of x. And so that's one strategy to reduce. If you have something that is not in terms of sine and cosine, just convert it to be sine and cosine, and then you can kind of see how things play out. Okay. Another strategy is if you see a trig function in the denominator, sometimes it's more helpful to bring it up. But if we bring it up, we can think of it as a reciprocal identity, right? So what's the reciprocal of cotangent? Tangent, right? We know that cotangent is 1/tangent. So 1/cotangent, we can just think of it as just tangent, right? We flip that to the top, that's just Yeah, anytime you see squares involved, like a raised to a second power, a lot of times it's, ooh, maybe it's a Pythagorean identity that I can involve to help me clean it up. So seeing that square there sometimes is a kind of helps us maybe move towards what we could use. Okay, another strategy is sometimes we can clean something up by using algebra. So you see multiple fractions. If you see multiple fractions, maybe we can bring them together. It's a little messy. Sometimes we got to involve common denominators. Okay, so anytime there's an adding or subtracting between terms, and they may not have the same denominator. If they don't, we have to find common denominators. Now, if they're being multiplied, it's a lot easier. Multiplication does not require a common denominator, right? Like sine of x times over 1 times cosine x over sine x. There's no need for common denominators. We can just cleanly match and cancel those out. But addition and subtraction can be a little messier. So let's see if we can clean this up, and then we can worry about two separate fractions, bringing them together. Okay, cosecant and secant. What can we rewrite these as? Sine and cosine. So cosecant, you can rewrite it as 1 over sine. Secant, we can rewrite as 1 over cosine. And then cotangent, rewrite as cosine. Okay, so now things are a little bit more familiar because everything starts with sine and cosine, but we still have some work ahead of us. If I think of this as two fractions here, sine and cosine, this can be merged together into one fraction. Okay, if I want to truly merge these fractions together, I need common denominators, right? I can't just subtract and put this together. What's the common denominator that both these fractions can go into? Okay. I need something big enough that both can multiply into, right? So sine would not be enough. Sine, maybe sine, you think sine is a common factor, but that's not what we want. We want a common denominator. We need sine and cosine. Okay, so sine x cosine x is the common denominator. Okay, so I'm going to put that common denominator here. And I'm trying to merge these two fractions so that they share the same common denominator, but I do need to potentially balance the numerator. Okay, are we okay here? Seeing that we need something that is large enough for both these individual denominators to multiply into. All right, sine of x would not be enough. Sine of x is not big enough to handle this sine x cosine x. Okay, so now it's a matter of trying to balance each of the numerators. Is there any change between this old denominator and this new denominator? No changes, so I can just bring down whatever I see in the numerator. There's no balancing necessary here. Okay, is there a difference between this old denominator and this new denominator? There is. What's missing? Cosine. So that's what I need to balance the numerator by. I need to multiply the numerator by cosine of x to adjust for the fact that this old denominator isn't quite matching my new denominator. So cosine times cosine gives me cosine squared x. Okay. You see how now we have common denominators? We can merge them into the same fraction. So I'm left with 1 minus cosine squared x all over sine x cosine x. So we're making progress because we have everything under one fraction, but there's actually something that we can do more here. 1 minus cosine squared x. Say it again?
Simplify cosine squared x.
Okay, and what do you mean by that? Okay, yeah, but you have the right idea. We're definitely working with that 1 minus cosine squared x. There's something identity-wise that we can do. So this is something that we have available. Remember, we have that sine squared x plus cosine squared x equals 1, right? So do you see something that we can do? What is 1 minus cosine squared x equal to? If I rearrange this. Yeah, sine squared. If I subtract the cosine squared from both sides, that's 1 minus cosine squared x, right? 1 minus cosine squared x equals sine squared x. That's a perfect replacement. That's going to help me do a little bit more cleanup. Right, so if I rearrange this, right, sine squared x is equal to 1 minus cosine squared x. And if I can see that relationship, I can replace the entire numerator with sine squared x. Okay, are we good there? Can you guys see that? Okay. So I'm going to replace that numerator now with sine squared x. Okay, so it's a little bit cleaner, right? Now that we don't have any subtraction, addition in the way, we can clean up and cancel out. So we can take a sine x away from both the numerator and denominator. So what are we left with? Okay, we're left with sine x over cosine x. Are we good there, right? This is basically sine x times sine x. We're taking one of them away. We still have one left over. No sine x left in the denominator. And then what's a clean way to represent sine x over cosine x? Tangent x, okay. One of the things that it's going to take some time to get used to is there's a bit of a kind of a puzzle-like feel to these problems where it's not like previous units where I can just say, okay, you can just follow the steps, right? Step 1, 2, 3, 4, and get to the answer. This is more like we have these tools in front of us, and some of the tools may end up giving us a dead end, and we have to kind of scrap it and just try something else to see until the puzzle pieces fit. So I find that sometimes with these problems, it's just a matter of getting a lot of repetitions, right? The more that you see, the more comfortable you're going to be able to kind of recognize certain patterns that will work, and you can potentially, stop yourself before you go too far down the wrong path. But I think it's just going to take time and practice problems. Okay. Okay. Another method. Strategy is factoring out common terms. So let's look at this expression here. Tangent times cosecant squared x minus tangent x. So we could convert everything to be in terms of sine and cosine, which maybe is a goal. But right now, I'm just seeing that, oh, there's two terms here, but they both share a tangent. If I can pull a tangent out, maybe that will speed up the patterns that I can see. Everybody see that? There's a common factor that is shared between these two terms. I'm going to take a tangent out. So if I pull a tangent, or basically if I divide a tangent out of both these terms, what's left out of my first term? Okay, just cosecant. And if I divide a tangent from this term, I'm left with what? Good. There's still a 1 left over. It doesn't completely disappear. All right, there's still a 1 over. So don't think of it as you're removing tangent away, you're dividing by tangent, right? So if you divide a term by the same term, it doesn't go to 0, it goes to 1. So this tangent of x is just kind of sitting out here. Not much we can do here, but this cosecant squared x minus 1, maybe there's something that we can do here. Do you recognize that? Is there an identity that looks like this? Okay, look at this one here. 1 plus cotangent squared equals cosecant squared. Is there a way to rearrange this so that we can find a substitution for that? Okay. So let me write that out here. So if I subtracted 1 from both sides, I can replace cosecant squared x minus 1 with what? This is the same thing as okay, so what if I subtract 1 from both sides? If I rearrange this identity, is that more clear now? Replace cosecant squared x minus 1 with what? Cotangent squared? Okay. All right, so tangent of x times cotangent squared of x. Okay, this is easier to work with, right? Because we know there's a relationship between tangent and cotangent. Cotangent, I can rewrite it as 1 over tangent. And notice that I'm choosing not to convert this to be in terms of sine and cosine because I have tangent here, so it'll be easier to see the recognition if I just convert it into something that looks like the other thing. Okay, what happens here? Tangent x divided by tangent squared x, I'm left with what? 1 over tangent x, right? That tangent x that remains is in the denominator, and I can replace 1 over tangent x as cotangent x, yeah. All right, another thing that is helpful sometimes is distributing conjugates. If I expanded this out, we're going to see something that's going to come out of it. If I distribute the secant x through, FOIL this out, I get secant squared x minus secant x plus secant x minus 1. The middle terms drop out. Right. And do you recognize anything that we can do with secant squared x minus 1? Yeah, we have that tangent squared plus 1 equals secant squared, right? So if I rearrange it, maybe I can find a replacement for that secant squared x minus 1. If I subtracted 1 from both sides, secant squared x minus 1 is the same thing as tangent squared x. So I can think of secant squared x minus 1 as the same thing as tangent of x, tangent squared x. Yes. Got it. Okay. So we have this property in front of us, right? We have tangent squared plus 1, which is the same thing as 1 plus tangent. 1 plus tangent squared x equals secant squared x.
Oh, okay.
So if I have that relationship, I can start with that and kind of move things around until I see something that I can connect it with. Okay. Okay, last one on this page. Is there a complex fraction? So when you see a complex fraction, potentially secant over tangent, you can think of it as, you can rewrite it as sine over, or in terms of sine and cosine. But anytime you see a complex fraction, we can always just bring the denominator up by multiplying by the reciprocal. So we know that secant is the same thing as 1 over cosine. And we know that tangent is the same thing as sine over cosine. Okay, that looks a little messy, right? You got a fraction divided by another fraction. But the way that you undo a complex fraction is you bring that denominator piece up. So if you want to bring that denominator piece up, all you need to do is multiply by the reciprocal. So flip it and then bring it up. So once we flip it, we know this goes away. And now it's a lot easier to see what relationship we can do here, right? What can we do to simplify this? 1 over cosine times cosine over sine. Cosines can just go away. So all I'm left with is, careful, right? We don't just say sine of x. This is really 1 over sine of x. And what's the same thing as 1 over sine of x? Cosecant. Okay. Next page. We'll just try to do as much of this as we can. But I want to walk you through some of these ones here. I'm going to write the identities up here because we're going to use them so much. It'll be easier access if I can just point to it. Okay, secant squared x minus 1. Let's see, if I rearrange it, secant squared x minus 1 is the same thing as what? Tangent squared x. You see that? If I just subtract the 1 from both sides, I get secant squared x equals tangent. Sorry, secant squared x minus 1 is the same thing as tangent squared x. We go down, see which one that matches. That matches with option P. Cross that out. Okay, 1 over sine of x. Same thing as, yeah, cosecant x. Sine x, cotangent x. What can we do with that cotangent to make it easier to pair up? Yep, cosine over sine, yep. Okay, what happens here? Sines cancel, I'm left with just cosine. All right, number 4, I want some room to work with this. I'm going to take up some of the space that I didn't need for 1 to 3. So, okay, let's talk about this here. This is the ones, these are ones I haven't quite gone over yet. But let's start it off here. Anytime I see sine squared or cosine squared or anything squared, I'm always trying to think, oh, maybe there's an identity that I can use. So is there an identity that I can use with that sine squared? Yeah, I can get it in terms of cosine, and that helps because if I get it in terms of cosine, that's going to at least have the same trig function as the denominator, right? So what can I replace sine squared x with? Yeah, so if I subtracted cosine squared from both sides, sine squared x equals 1 minus cosine squared x. So I want you guys to put that up here because we're not quite done yet. All right, the temptation is to start canceling things out, right? 1 goes away, cosine goes away, maybe we're just left with negative cosine x. But it's not as easy as that. Why? What's the issue here? Why can we not just start taking stuff out? Say it again?
The 1 term.
Okay. why can we not just cancel one of the cosines out again?
1 squared.
No, something else that I want you to verbalize for me. What's causing us to not be able to? What if it was, I mean, what if it was 1 minus cosine x over 1 plus cosine x? That's still an issue. We still can't cancel. You guys know why? Okay. It's attached to addition or subtraction. Anytime you see addition and subtraction connected to something, we just can't remove it. It's not as easy as just, now if this is being multiplied with something, or if it's completely by itself, then you can be free to cancel out. But if there's any addition and subtraction involved, I know it looks like we can, but we're breaking rules and we're not getting the same value. Okay, does that make sense? Okay, we cannot cancel across addition and subtraction as much as you would like to, because it looks like such a easier thing to do. So what needs to happen is we need to play with this 1 minus cosine squared x. Okay, and the way we can play with it is, let me show you here. This is going to have to be involving difference of squares. Okay. So to remind you, difference of squares is where I can break perfect squares down into a minus b and a plus b. Right, perfect squares can be broken down. Same thing here. If I have 1 minus cosine squared x, 1 can be broken down into 1 and 1. Cosine squared x can be broken down into cosine and cosine. So 1 minus cosine squared x can be broken down into 1 minus cosine x times 1 plus cosine x. Okay, do we see that relationship there? They're both perfect squares. We can break them down into its individual parts. Now that you have your individual parts showing, now you can begin to see how we can cancel things out. So 1 minus cosine squared x is 1 minus cosine x times 1 plus cosine x. Now we can cancel out. You see how these 1 plus cosine x are nicely separated with parentheses with no addition and subtraction connected to it? So now these are free to move or free to reduce. So do you guys see that distinction here? We can reduce these, but we can't reduce these. Okay, so 4 ends up being, let's see, 3 ends up being Q, and 4 ends up being W. Okay, questions here? Okay, let's just do a few more here. Number 5. 1 plus tangent squared x. Do you see anything that we can do here? Any identity that we can use? Yeah, looks like it's already nicely set up, right? So secant squared x. Okay, number 6, cosecant squared x minus cotangent squared x. Anything here? Just 1, yep. If I subtracted cotangent squared x from both sides, cosecant minus cotangent squared is just 1. Okay, that's good enough for today. No homework. We'll just pick this up tomorrow, okay?